Okay, so this is, we move now into a new chapter, chapter 10, which is about curves given by parametric equations. And this is going to greatly generalize the types of curves we can look at. And parametric curves, which I'll explain in a moment, are really in some sense, the best way to write down equations for curves. Okay, so 10.1, parametric curves. So here's the idea. So usually we are looking at curves of the form given by the graph of a function, y equals f of x. So this would give a curve, but not every curve is of that form. For example, we can look at the circle. The circle, usually we give it the equation x squared plus y squared equals 1, but that's not the graph of a function. Why? Because it fails to satisfy the vertical line test. So there's yet another way then to specify more general curves as follows, parametrically. So the idea is this. Think of yourself as a bumblebee in the plane, and you're moving around in time t. So at every time t, you're at a point on the curve, x of t comma y of t. So the equation, a parametric equation, is an equation of the form x equals x of t, y equals y of t. And then sometimes t can be specified as lying in some interval or not at all. So for example, t could be between a and b, or t could be just greater than or equal to some number a, etc. So let me do some examples. Okay, so this is the general form of a parametric curve. Okay, examples. Okay, so the first example that I'd like to give is x equals cosine of t and y equals sine of t, and then let t vary between 0 and 2 pi. So how do we plot this? Well, we can note that cosine t and sine t satisfy the equation cosine squared theta t plus sine squared t is 1. So x squared plus y squared is 1. And since t is going from 0 to 2 pi, it starts with t equals 0, which gives you the point x equals 1, y equals 0, so there's 1, 0. And you're moving around the circle at 40, when t is pi over 4, you're going to get cosine pi over 4 comma sine pi over 4. That's this point here. You're moving around in a circle around, it's a unit circle, and you're moving in this direction. So parametric curves have a direction of motion on them. And so after we get back to 2 pi, to t equals 2 pi, you're actually where you started. So actually, there are other equations. Many formulas give the same underlying curve that you would see. For example, we could have x equals sine of t, y equals cosine of t, and then x squared plus y squared is again 1. And maybe we want t to again go from 0 to 2 pi. And in that case, you would get a unit circle again, but when t equals 0, you would be at the point 0, 1. So you're starting off at this point and you're going around the circle like this once. So this is a different formula for the same curve, different parametrization. This is called the parametrization, the actual formula. We also have even different parametrizations which start at the same point. For example, x equals cosine of 2t, y equals sine of 2t, where t is between 0 and pi now, not 2 pi, because I've sort of doubled the speed I go around the circle. This is again going to satisfy x squared plus y squared equals 1. And you're going around the circle like this again, but at twice the speed. So that's going to give me the same underlying curve. It's a different parametrization. Okay, so what if you have a classical function y equals f of x? How can we make it into a parametric curve? Well, we can set x equal to t, and then y would be equal to f of t. So this would be a parametric expression for the curve given by the graph of a function. So that's an example also of a parametric curve. So any function gives rise to a parametric curve of this form. For example, y equals x squared, you have x equals t, y equal t squared. That's going to give me the parametric form of a parabola. Okay, so I want to talk about another example of a kind of parametric curve called the cycloid. This is in the book. So how does that work? So the cycloid is a curve which has which works like this. Suppose I took a coin and I put a point on the coin, and I let the coin is on its rim, and I let the coin move in a straight line. Oops, let me get rid of that. I let the coin move in a straight line in this direction, so I let it move in this direction. So what happens to the curve, to the red point as the coin rotates? Well, it will give a curve, and the curve is going to look something like this. Okay, so the problem is to get a formula for the cycloid, and so I'm going to give you a way of parametrizing the cycloid. So what I'm going to do is I'm going to take the coin and blow it up. So here's the coin, and let's call the center of the coin C. Let's put the origin here, and let T be the point that it touches the ground, T for touching. Let P be the point that we've rotated a little bit. Let's assume the coin started at the origin. So now the point P would be here. This would be P. And let's consider the following. I'm going to draw some line segments in. So the coin has been moving for a little while, and there's an angle of rotation. Let's call it theta. And let the radius of the coin be r. And then I'm going to put in some more lines here. Suppose I put in this right triangle here. So theta, by the way, was the angle, the central angle that was made. Theta would be this angle here. So let me indicate that. That would be theta. Okay. So so then let's call this point here, let's call it Q. Okay, so theta is the angle of rotation. And so theta is 0 when P is at the origin, because I'm assuming the point P, that we start off with P at the bottom. So theta equals 0 if P is at the origin. Okay, and let the coordinates of P we'll call XY. So P will be the point XY. Okay, so what are the coordinates of this point XY? Well, let's figure it out. Okay, so first of all, X is this horizontal segment here. That would be X, and the vertical segment would be Y. So X is in yellow. Oops, that's not yellow. but x is here, and y is this vertical segment there. Okay, so what is x? Well, the amount that we the first thing I wanted to figure out is how far has the coin traveled? Well, the coin travels the arc PT on the circle. Here's the arc PT. So the arc of PT given by the circle. Well, according to the length of an arc is given by the radius times the central angle. So that would be r theta. And that's the same thing as the distance from the origin to t, right? So OT. So it's the length of OT. Okay, so r theta is OT. Now, what are the coordinates of the point x? Well, x, if you stare at this, it's given by the distance from O to t. So x is OT minus the distance from P to Q. P to Q is this blue is indicated in blue. So the distance from P to Q. Okay, but what is that? Well, OT we said was the arc of PT, which is r theta. And the distance from P to Q we can compute using this right triangle. It's going to be r times sine of theta. Likewise, y is given by this little green segment is the difference between the center, the radius r, and the vertical distance from C to Q, which is C to Q has vertical distance given by r times cosine of theta. Okay, so now we're pretty much done. I'm just going to indicate the final answer here in this little box. So it's going to be given by x equals r theta minus r sine theta, which is r times theta minus sine theta. And y is r times 1 minus cosine of theta. And here theta is any real number. So minus infinity is less than theta is less than infinity. So this is the cycloid. This is a parametric form. So I'm not using time anymore to parametrize. I'm using the angle theta. Okay. So I thought I would do some examples from the exercises. So here's exercise number 12 in the book in section 10.1. So it's identify the curve. So x is 1/2 cosine of theta, y is 2 sine theta, and theta is between 0 and pi. Okay, so the way I would do this is stare at the formula and see how we can get it in terms of x and y alone. So if we take 2x, that's cosine of theta. And if we take y over 2, that's sine of theta. And that tells me that 2x quantity squared plus y over 2 quantity squared is 1. So in other words, 4x squared plus y squared over 4 equals 1. And that tells me it should be an ellipse, except there'll be one little change there, you'll see. Because theta is going from only 0 to pi and not 0 to 2 pi, it's going to be half an ellipse. Which ellipse? Well, when y is 0, x squared is a quarter, so it's going from minus a half to plus a half x. Okay, and when x is 0, y is squared is 4, so y is going from 2 to varies between minus 2 and 2. And now when theta is 0, x is a half, and y is 0, so it's starting off here, and it's winding around. And then when you get theta equals pi, it's halfway, and this is the curve in green. So this is a half or a semi-ellipse. I would call this a semi-ellipse. So that's our curve. Okay, let's do another one. Here's another example. Let's try example. don't know the number of this, it doesn't matter. I'm just going to give you the question. So x equals e to the t, y equals e to the minus 2t. So what curve is it? Well, you stare at it and you see that if I take x to the minus first power, that would be e to the minus t. But we don't have e to the minus t for y, we have e to the minus 2t. So we could square both sides to get x to the minus 2 is e to the minus 2t, which is equal to y. In other words, y equals 1 over x squared. Okay, now y equals 1 over x squared is this curve here. However, we should go back and realize that the way we've done this, x can never be negative because e to the t is negative, never a negative number. So in fact, what you get is the right-hand branch of the function y equals 1 over x squared. That's going to be the curve. Okay, so that's that example, wherever it is in the book. Okay. Okay, so I'd like to consider problem number 28. Now, this is actually a pretty tricky problem, and it takes a while to get used to thinking in this particular way. So it's a matching question. It says, match the parametric equations with the graphs labeled 1 to 6. Okay, so let's, this is actually from edition 8 of the book. I didn't pull this from edition 9 because edition 9 has parts of this problem on two separate pages. It would be hard to follow. Okay, so let's try to do the matching with as little, without actually using a graphing device. Okay, so the first thing I'd like to point out is that if we stare at these graphs, some of them have different properties than others. For example, graph number 3, graph number 6, graph number 2 are all bounded. They exist in a bounded portion of the plane, whereas graphs 1, 4, and 5 are unbounded, it seems like. Okay, so let's look at E. Okay, let's look at E. So that's x equals t plus sine 4t, and y equals t squared plus cosine 3t. Now sine 4t and cosine 3t, they vary between -1 and 1. So when t gets very, 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 very big, that's like negligible. So you're looking at x equals t roughly, and y equals roughly t squared. Well, that's y equals x squared. That's like a parabola, right? It looks like your standard parabola in the xy plane. And so these little sine 4t and cosine 3t, these are little correction terms. And so what you're going to get is something that looks like the standard parabola. And the only picture that looks like the standard parabola a little bit, that has its properties, is picture number 4. So E is picture number 4. That's what I would say. Okay, so we've now gotten E out of the way. We've also gotten picture number 4 out of the way. Okay. I would like to draw your attention now to equation F. That's x equals sine 2t over 4 plus t squared, and y equals cosine t over 4 plus t squared. If that 4 plus t squared was not in the denominator, you would have x equals sine 2t, y equals cosine 2t, which would be a circle as you move around. Well, this is not a circle, but because the denominator is changing and it's getting bigger as t gets bigger. So what you're doing is you're shrinking what would be a circle. The radius of it would be getting smaller and smaller. So it's going to wind around the origin, but it's going to shrink as t gets bigger. And the only picture that looks remotely close to that is picture number 3. So F and 3 are related, it seems like. Okay, so there we go. F and 3 are related. Okay, so let's move on to figuring out the rest of it. So now I suggest we look at equation B, x equals t squared minus 2t, and y equals the square root of t. In that case, the way to think of this, first of all, here x and y can be unbounded. And since we've taken care of picture number 4, what's left over is pictures number 1 and 2. Now, let's look at the places where x can be 0. X can only be 0 if t squared minus 2t is 0. And that would be the same thing as saying as t times the quantity t minus 2 is 0. So t would be 0 or t equals 2. Would be the two places where x is 0. And now if x is 0 at t equals 0, then y would be 0. So that would be the origin. And if t equals 2, then y would be the square root of 2. So the picture that best reflects that is picture 1, because picture 5 does not even go through the origin. So picture 1 should correspond to equation B. Now, by process of elimination, the only thing that's left over that's unbounded would be equation A, where x and y can get as large as you want it to. And the only graph that's unbounded is picture 5. So A and 5 have to be matched up. So that's that A and 5. Okay, so now we're left with two different things left over, picture C and equation C and equation D. Now, equation D is very regular looking, whereas equation C is much less regular looking, in the sense that if I take t and replace it with t plus 2 pi, I get back to where I started. By the way, the only graphs left over are graphs 6 and 2. Furthermore, notice that cosine 5t, when t is varying from 0 to 2 pi, is going to cross so x is going to be 0 between 0 and 2 pi. Cosine of 5t between 0 and 2, when t varies from 0 to 2 pi, is going to take the value of 0, that is x will be 0, 10 times in the interval from 0 to 2 pi. And if you look at graph number 6, you see it crosses the y-axis 2, 4, 6, 8, 10 times. So therefore, picture D, equation D should correspond to graph number 6. And then by process of elimination, you're left with equation equation C, which is harder to understand as being closely related, which should match up with equation graph number 2. So there you go. And I'm going to write this down on another slide for posterity. So you have A, B, C, D, E, and F. And you have A we decided was 5, B was 1, C was 2, D was 6, and E was 4, and F is 3. So that's the matching up there. Well, I think that's enough for today. And till next time.